அந்த கணக்கு எடுத்து போயிட்டாங்க.
என்னாச்சு?
இல்ல சார், இந்த கணக்கு தான் சார் செட் ஆகும். ஏன்னா இது போடுறதுக்கு சார்ஜ் போடுறதுக்கு ப்ளஸ் ஆடியோக்கு இதுல டைப் சி இருக்கிறதுனால.
யாரும் வேற எடுத்துட்டு போயிருந்தீங்களா?
கரெக்டாக குமார் சார் கிளாஸ் முடிச்சுட்டு லெக்சர் எதுவுமே கொடுத்துருக்கீங்களா?
ஏன் 2 பேருமே இப்போ அது இருக்கேங்க
ஹேண்டில் இருக்கு. இது
அதுவும் கொடுங்க. நான் கொடுக்கும்போது பண்றேன். அது அவங்க okay, I think okay. Diganta is here.
Hello. Hello, can you hear me?
Yes, Diganta, I can hear you.
Okay, okay. So, let's start. Is the recording live? Okay, yeah. So.
This meeting is being recorded.
Okay, Diganta. So you could, you have till say 10:35 right now. So 10 minutes, I said 10:45. Okay.
Okay, sure, sir.
Yeah. Hello.
Yeah. I can hear you. Yeah. I'll not take. I'll not take more than that. Yeah, sure.
Yeah, but I think for some reason you're very faint. The last time also you were a little bit choppy. Okay. Can you speak up now?
Is this slide
Yeah. Now
visible?
it's fine. Yeah. Please go ahead.
Okay. Yeah. So, firstly, are there any questions from last time that anyone wants to ask before the? So, I just have one slide, which is this a few points that I wanted to make regarding overfitting, which I was discussing last time, but I think yeah.
Yeah, you could make full screen if you wish.
Yeah, I think this is the.
Yeah. Oh, I have to. Sorry. I think it's my mistake. Okay. Yeah, we are fine.
Yeah.
Anybody have any questions specific? Oh, no, you go ahead. No questions from this end.
Okay, sure. So, so we were discussing this idea of overfitting last time. So the idea of overfitting is that, suppose if you have a model which can capture a lot more information than what you really intend to capture from the data set, right? So what happens in that kind of a situation? That is basically the kind of idea behind overfitting. So, for example, consider that this situation where we have a polynomial, right? So we have some data that is, roughly speaking, distributed along this gray line, and these blue points are my actual data points, while the red points are going to be data that I'll get to see once I actually deploy the model, right? So while training, I'm seeing only the blue points, but then in real life, when I try using the model, I'll see more and more new points along the same sort of distribution, right? So those will be my red points, let's say. Then if I were to train a polynomial, depending upon the degree of the polynomial, we'll get various different curves, right? So here degree can be thought of as like one measure of complexity, like how much information can the polynomial contain. So if we were to train to perfection a degree 1 polynomial will probably get a line like this. If we were to train to perfection the degree 2 will probably get something like this. And once we start training things like degree 3, you can see that we're getting polynomials that are very closely aligned to this this gray line, right? So for example, with this degree 3 polynomial, we can really very closely approximate the original gray distribution, right? But remember, we don't get to see a gray line, nor do we get to see these red points, right? During training, all we really have are the blue points. And you'll notice here that we still have some error for the blue points. So it might feel intuitive to say that, okay, let's try degree 4, because, if we allow for more degree, then we'll essentially allow the line to curve more and hit more points, right? So we can do that. And we can keep trying higher and higher degrees. And eventually we can try degree 9 polynomial, which it turns out will actually hit all of these points, right? So there I think, essentially 10 points here. So if you try a degree 9 polynomial, you can basically make it fit through all of these points, right? So now from the perspective of just minimizing loss on the data set, this will actually have zero loss. This is the best possible fit that you can imagine, right? Remember that we don't get to see this gray line or the red points while training. So from the point of view of minimizing the loss, when we're doing the training, this will have nearly zero loss, right? But if you look at what is happening with respect to these red points, this line is actually much farther than this particular example that we had, right? In fact, if you were to deploy this will do much worse than this one on the actual real life data set, right? This one is much closer to the original distribution that we intend to capture. Well, this is actually much farther than that, right? In some sense, here, what we're doing is we are spending a lot of effort trying to capture whatever noise we have on top of this data set, right? This basic phenomenon is called overfitting. One way of understanding is that whenever you're trying to fit to some distribution, what you have is like a noisy view of the distribution, right? What you're really seeing is some set of samples and what the value of for the function that you're trying to capture is at those samples, which will always be some noisy view of the distribution, right? So the question is always going to be that, okay, whatever you have learned, is that actually the real value at the distribution? Have you really learned the distribution, or have you really learned the noise on top of the distribution, right? So this is the situation with overfitting, where you can essentially learn this noise, and what that will lead to is a situation where you have something like this going on, where you're seeing very low loss on your training data, but once you try it out on the real world, the loss comes out to be very high, right? So this phenomenon is called basically overfitting. So the question really becomes, how do we detect overfitting, right? So okay, fine, this is something that can happen, but then what do we do when we're training a network to sort of detect overfitting, right? So the idea being detect overfitting is two things. So firstly, we would want to split our data set into two parts. So we would want to say that we will have a training data set and a testing data set, right? And the idea is that we want to simulate this situation where, when we deploy the model in the real world, we will get to, or we will have to see the model run on data points that we have not seen before, right? So we simulate that by saying, okay, let's actually take some of the data that we have and keep it aside. We'll not train the model on that. We'll never calculate a gradient with respect to that, right? So we never do any minimization and optimization with respect to those points. That separate set of points from the data is called this testing data set. And the points that we keep on the other side is called the training data set, right? And then what we do is that on this training data set, we will do gradient descent. So when we do gradient descent for training, this is where we calculate L theta and delta L theta, delta theta, and so on, right? This one will not calculate gradient descent with respect to it. Correct? But what we will do is we will keep measuring the accuracy with respect to both of them, right? So the idea with measuring this accuracy is not so that we can do gradient descent to reduce this accuracy, but keeping track of this accuracy of the training and testing loss will actually help us to detect when we are hitting overfit, right? So if you were to keep track of this accuracy, what you would get to see is a graph that looks something like this, where the idea is that this guy is going to be your testing loss, and this guy is going to be a training loss, right? So why would this happen? Because as you are training, up until a point somewhere, both your testing and training losses will go down, because at that point you're just learning the original distribution. So you can sort of think of it as sort of the first three slides here. So as you're fitting your distribution more and more accurately, you're increasing the accuracy in both the actual blue points and the red points, right? So both your training and testing loss is going down. But then after a while, what happens is that now, no matter what training you do, what you're ending up learning from this point forward is just the noise in the data, right? So from this point forward, you're just sort of ending up learning these lower six kind of pictures, right? So you have situations shown in the lower six pictures. You're just learning the noise in the data. And so since you're learning the noise in the data, if we take a different sample of the data, which is basically what the testing point is, right? It's a different sample where the noise is different. The underlying distribution might be the same, but the noise on top of it is different. Then what you would get is, a higher loss on that, right? So you'd actually do worse. So what you'd start to see is that, okay, while training loss is going down, testing loss actually starts to slowly go up or stay the same for a while and then slowly go up, right? So this is the sort of method which people usually try to do to capture when overfitting is happening. So they look for a graph like this, and they look for this sort of departure between the training and testing loss curves, right? Now, a point that I want to make is that in real life, the graph may not be like, if you actually do an experiment training in real life, it may not be this nice and perfect in the way that I've seen. Usually, the graph is itself very noisy. It's not a linear process, right? But you can, you will basically be able to see a situation where you can see that, okay, the training losses kept going down, but testing losses not, right? And if you do find a situation like that, that is a clear sort of sign of overfitting. And in general, people will not train it all the way up till the point where training loss is down to very low numbers, where testing is not going down anymore. Right? Whenever the improvement in the testing loss stops happening, whenever you get to a point where you sort of saturated the improvement in the testing loss, people stop training, because more likely than not, everything from that point onward is going to be sort of the rightmost part of the graph, and it would indicate overfitting. Right. So this is overfitting. But if you think about it in a different way, this is actually, you can sort of think of it as a symptom of a deeper problem, right? The deeper problem being that when you train a neural network, you don't really know a priori what it has learned, or any machine learning model, right? with any machine learning model, all that you have, both during training and later on during evaluation, is going to just be the data, right? It's just going to be some samples that is going to view your data set, right? So whatever that a network will learn is going to be some function with respect to this data. And you don't necessarily know whether or not that is what you want to capture or not, right? So you might want to capture, so you might be sort of training a network to capture some concept like, let's say, road sign detection, right? But what you really just have is input output examples. So you just have a bunch of examples of road signs. I mean, as a human, maybe you know exactly what you want in terms of being able to detect road signs, but you can't really capture that into code. What you have instead is an example of road signs, which means whatever you at the end of the day, what you'll have is a model that does good on some examples, right? And fundamentally speaking, this can't really tell you anything about what will happen in general.
Yeah, I think so. This is Diganta. I mean, this you're feeble. Okay, so you have to speak into the microphone or close
Sorry,
it.
sorry. So is this better? Sorry, from where should I
Yeah,
repeat?
this is better now.
Yeah.
No. You continue.
Okay,
So
sure.
go to
So
11 o'clock. Okay, or
no.
you know,
I'm just done in 1 minute.
no. You can take 10 minutes. So if indeed, these things might be important because they will also be working on an example for training and so on. So one question I had was, what kind of support like a tool like TensorFlow gives to avoid overfitting? Okay.
Yeah. So I think with respect to most of these tools, they don't have some precise support in the code to avoid overfitting, because um, that is more of something that you would configure the creating a loop to itself do. So the tool will usually have, so TensorFlow or PyTorch, both of them usually have utilities that will help you to split the data set into training and testing. And most datasets that you can, like, most clean datasets that you can do learning on there sometimes come split already into training and testing. And there's again utilities to measure accuracy, but you will have to sort of plot this graph. I mean, there is utilities to plot graphs and so on, but one has to sort of plot this graph and sort of keep track of when it is that this departure is happening, right? There is no nice
Pretty much what you have to do is, as you train
yeah,
on your training data,
you have to keep
every month,
measuring
you
both
will
those
have
things.
to also test the thing as to what the accuracy is on your testing data and see how these things are varying. And if there is a point at which there is divergence, you stop
Exactly, yeah.
training them.
Yeah.
Is that the idea?
Yeah, that is the idea.
Yeah, okay.
Yeah. Right. So any other questions regarding overfitting?
Okay.
So
None.
yeah, so as I was
Go ahead.
yeah, sorry. So as I was saying, this in general can be thought of as a symptom of a bigger problem, which is that in general we don't know what a model has learned, whatever
Yeah,
whatever it has.
I think you have to speak in. I mean, I don't know what
Okay.
you're doing, but you kind of gradually become feeble.
Hello. Is this
Better, but yes,
okay, just a second.
whatever you're doing now, stick with it.
Okay, yeah. Uh just increase the volume. Yeah. Okay, so like I was saying, this this is a general symptom of a deeper problem, which is that whatever a neural network learns is going to be with respect to some data set at the end of the day. And at the end of the day, we won't really know what it precisely has learned, right? Because all we know about the neural network is how it performs on the data set. We hope that that will generalize beyond, but that may or may not be the case, right? It's at all not clear a priori why we should expect a neural network to generalize beyond the data set. It does in most cases, but in many real world cases, it also does not, right? So one way of sort of
Yeah.
interpreting, yeah.
So, sir, in like foundations of machine learning course, we learn that to overcome this problem of overfitting, you take a hypothesis class which is agnostic pack learnable. Is this gonna come in here anywhere to help in like real world scenarios?
Yeah, the way you can sort of in that sort of a scenario, if you take up a hypothesis class, there is agnostic pack learnable. I mean, the question is whether you can sort of detect whether a neural network is going to fit into that sort of scenario, and
Yes.
more practically, whether the situation that you have with this training testing split can simulate that kind of a scenario, right?
Yeah.
Yeah, so the idea is that this is basically going to try or come close to attempting to achieve that. And practically, usually with neural network, what people do is from at least my understanding, to try and achieve that is this training testing split. But if you have more models that are so you can sort of go this other route, right? You'll say that you'll not have this complicated general model of a neural network, but you'll have models with fewer number of parameters and sort of designed from a more principled point of view, where you can really try and understand what is it exactly that is happening with respect to overfitting, and how much representation capacity that you have with the model, right? So that is another route that you can take. Does that answer your question?
Yeah, I mean, if a more like if a hypothesis class is agnostic pack learnable, then we are kind of approximately sure, right, that we will not be overfitting. So do we?
Yeah. But the question is then, how do we know whether that is the case for a neural network, right?
Yeah.
Right. So it turns out that like applying any of those so those are fairly complicated notions to apply on any model. So in particular, applying them on neural network, from my understanding, it's at least quite challenging, right? Because yeah,
Okay.
but in general, practically speaking, this is what people tend to do.
Okay, Diganta, 5 minutes.
Yeah.
No longer than that.
Yeah.
Okay.
So so intuitively, there is another you can sort of view this as like I was saying, you can sort of view this as symptoms of another
You
problem.
have to speak into it. I don't know. I mean, otherwise,
Hello.
Hear off. I don't know.
I'm sorry about this. I am speaking into the mic. I have not changed anything on my end.
Okay. So maybe it's intermittent for whatever reason.
Yeah. I'm sorry. Yeah, but yeah. So
Speak up a bit. Okay.
yeah. So there is another sort of way in which a similar deeper problem can appear, which is this brittleness, right? Which is that if you were to change the training data distribution even slightly, you can get a huge change in your network. And again, if your neural network is overfitting, then it's going to be brittle, because then you have a situation like this over here, where of course, if you shift one of the glue points, the behavior of the line shifts by a lot, right? And the same sort of intuition holds that if it's not overfitting, then it's probably capturing some underlying distribution. So if you were to change the distribution without changing the
Can
training
you
data
define
distribution.
what brittleness is?
Yeah, so the idea is that if you any sort of classification system is going to be brittle if it's going to be highly sensitive to the training data distribution. So imagine that if you have training data that is not entirely clean, like someone has sort of poisoned the training data with some points that are out of distribution, right? So for
So you're
example,
saying that even small changes to the training data, small perturbations to the training data can have wild outcome in terms of accuracy. Is that a good way
yes.
to?
Yeah. That is what I'm saying. And when I'm saying changes to the training data, I'm not saying changes to the input during evaluation, but I'm saying changes to the training data that it sees during training. So imagine adding one more blue point to this graph somewhere, right? If that causes my neural network to learn something completely different, then I would say that the neural network training process is brittle.
Yeah. So how do you propose? How is this related to overfitting, or if at all?
So the idea is that in both of the cases, we are essentially learning some noise that is there on top of the original distribution, right? So we always have some underlying distribution that we're trying to capture. But in both of the cases of overfitting and brittleness, what we are ending up doing is we're getting swayed by this noise that is there on top of it, right? In overfitting, there is this particular noise of the particular input sample that we have. And here there is, there's whatever noise is being added to the data set by this poison
Okay,
point.
so in the interest of time, I think what we should do is,
And
you should just describe. Okay, I think we have given.
This is all I had. This is all I had.
A lot of details. If there are, certainly this brittleness is a concept, and then if there are papers that address
I'll send some references,
especially from that combine. I mean, that evaluate brittleness using rigorous methods. Even if not formal verification, we can actually identify them. If anybody is interested in studying it more, okay. Robustness we've already talked about.
Yeah.
Therefore, since it's 11, shall we?
So this is all I had. So robustness I was not going to repeat anyway, because that is we have already talked about.
This certainly is something that we should look at.
So with respect to brittleness, in fact, I think that there is a few people who are trying to look at verifying brittleness or measuring brittleness, bounding brittleness using formal methods techniques, but they usually don't apply it to neural networks, because so they do apply such techniques on some simpler models like linear regression and
I see.
decision tree kind of models. Yeah.
So we can keep that in mind, okay?
Yeah.
And then when we come up with the final list of papers with topics, which will, by the way, we plan to do within the next week or so, okay? So we should, the instructors, we will sit together and then kind of put more structure into the list of papers that we have published, okay, in terms of topics and so on, so that, and then we prioritize what we would like to study in the course, and try to come up with some kind of a compromise that will accommodate your interest as well as our goals, okay? And that we will do very soon, so that and then you can, assignment has to be done of the papers, I'm hoping by next week, so that you can start reading those papers in the area. So while we cover some of, continue to cover some of the more basic stuff, including, basic concepts of formal verification, as well as some basic techniques that people have used for neural network verification. And I expect and those things to be, the next couple of weeks at least, we'll need for covering those basics. But the assignment of papers to complete even before that, so that you could be looking at the thing. So that we will do. So any other questions on this gradient descent and so on? So yeah, one more question here. Yeah.
Sir, does brittleness Hello? Yeah. So does brittleness basically arrive because the training data is not sampled from the same original distribution in and like this the data that I'm collecting is not like independently sampled? Is that why it's happening?
Yeah. So usually when people define brittleness, they say that, let's say that the train data is they use the term poisoned, as in, so you've got two distribution. You've got some training data, and you've got some original distribution, and you've got some completely different distribution, and you're just sort of mixing in a few data points from a different distribution into your training data. So that is what people usually mean with brittleness. So for example, I mean, I might have some script to collect some road signs and scrape some road sign images from the internet, train on. But maybe that script is like buggy in a very subtle way, where suddenly one of those images just contains a tree, doesn't contain a road sign, right? And it might be just one or two in like a few 100,000 images, but it is one or two, right? So then that will be sort of a poison data set. But if a neural network is because of just those two examples, my training process completely gets detailed, then it is sort of a brittle training process. So yeah, so there you have some real world distribution of road sign images, but then we have some poisoned data set points which are from a completely different distribution.
Okay.
Yeah, I think we have to look at this a little bit more carefully because it is also not completely clear to me. I mean, if it is, some people define it as, okay, even when you, maybe it is all related to this training data distribution. I mean, I've seen this thing being defined as you remove a couple of data from your data set or a small set from your training data set, and it behaves wildly differently.
Yeah. So even I think the most general definition that people propose is change in general, like remove points, remove some points, or relabel some points, or add some points. If it changes in any of them, it is usually termed as brittle. And I think in various different specific scenarios, you can reduce the analysis to checking one of these three kind of modifications that you data set.
Yeah, as opposed to, whereas robustness, the way they've defined is you add some perturbation to the input. Okay.
Yeah.
Robustness is about the test data. Okay. Perturbations to test data, whereas brittleness is as it applies to the training process. Correct?
Yeah.
That is,
That is how I understand.
Difference. Okay. Okay. Yeah. Shall we agree to end this part of today's lecture here? Okay. And then revisit it, especially with respect to brittleness and robustness. You know, if we find some papers and there is interest, papers that address this particular topic, and if there is interest, okay, that we can do some homework to see if there exists something that in the literature that is worth looking at. Yeah, when we make the new and the final list of papers. Okay. Okay, so now I'm going to switch gear and I will take over. So Madhukar and Diganta, this is something that is basic stuff for formal verification and so on, like in horologic. So I'm not going to insist that you have to stick around. So if you want, you could leave.
Yeah, sure, sir.
Yeah. Okay. Sure.
What I want to say. And
I'll stop sharing.
Yeah, do that. Yeah, I mean, I see, and also here you have taken in ARPAN, a couple of you might have seen. For you, it might be a little bit of a recap, but please stick around and see if you can give the thing. For all the rest of you, you have not taken formal verification, right? So pay attention, okay? And I will go slow with examples, and you please ask questions, yeah? Okay. Hello? I'll keep it here. Oh, but you don't need this. Okay, we don't. So, Guhan, are you there?
Yes, sir.
Yeah, you can hear me, no?
Yeah.
Okay. Okay, you can see my screen, Guhan, there?
Yes, sir.
Okay. Maybe that be better. Yeah. Okay. Can you read it from there? If not, you may want to move. Okay, so this is the example that you've already seen. Okay, this is actually the one. It's the modified version of the example that you're supposed to be working on. Okay, and I want especially those that have not taken the. I mean, anyway, it is. That Z3 is an assignment for everybody. So even though it may be routine and for you, I suggest that you submit. Okay, work on that and then submit. But in any case, I'm giving the thing solution here. So this is how it's been modeled as a formula. Okay, so that is intended. Okay, to capture the input-output behavior of this neural network. And there are, as you can see, the linear transformation parts of it. Here, the linear transformation is very simple. And the ReLU is defined using implications, okay? So what I'm trying to yeah. So in general, formal verification of any kind of artifact. By artifact, I mean an artifact could be a program. In this case, it's a DNN. Okay, it could be hardware or any combinations of things. So first step is model behavior of the artifact. I mean, that is the design under verification as a formula. In this case, since the neural network computes, we are modeling the input-out behavior. It's a function that maps inputs to outputs, and we are defining that function DNN by means of the formula. Okay, so that function is defined over several variables. So any satisfying instance of this is included in the is a valid thing for the function map. Okay, so the second step is you model expected outcome of behavior also as a formula in the logic. So in this case, so for example, you want to check that the output is in the negation of the input. That's the expected behavior. So you model that. This is the property that we want to verify. And then you construct what is called a verification condition, which when checked, either satisfiability or validity, it guarantees that your property is met. Okay, so in this case, since we want to verify that the DNN, for all inputs, the DNN obeys this property, we make the verification condition. This is the property that you want to verify, okay? And this is the verification condition, okay, which says that assuming that the DNN, my model of the DNN behaves as expected, then this is valid for all values of inputs and outputs, okay? So this is expressed as the validity. And with a SAT or an SMT solver like Z3, validity is checked by taking the negation and proving that it is unsatisfiable, okay? So if there is violation of this unsatisfiability, any satisfying instance will be a violation to the property, and that's how it is done. So that's just a recap. Okay, so all that, okay, yeah, so now I want to take a program verification point of view. So what I'm going to do is there are lots of examples in the slides, the presentation that I have, that I'll be uploading, okay, which kind of covers whole logic in a more formal program verification point of view. Here, since we are looking at it from DNN, I'm using this kind of treating the DNN as a program and seeing how the same verification can be done while treating this as a program. So this DNN can all be captured as a sequential program. Okay, so all the linear algebraic transformations are expressed as some assignment statements, and the ReLU part is expressed as if then else. Okay, and the variables here of this program include the input, things to denote, variables to denote the input, the output, as well as every internal node. Okay, so this is fairly easy for you to understand. So now, and this property that you want to verify is now specified as in two parts. One is as a precondition, okay, which formalizes the assumption on the inputs at the entry point. And what you want to verify is that when you reach the exit point, okay, for all inputs that satisfy my input assumptions, when I'm at this point, the given condition as post condition satisfies. Okay. Yeah, as you can see, this DNN, when viewed as a program, the program is very restricted as a program. Okay, when you look at some normal program, so here every variable is assigned at most once. Okay, so unlike in programming languages, you can have x gets x plus 1. The same thing can change. Okay, that is not the case here because there is it's more like if you're aware of functional program, okay, it is like that. Okay, so that's how this thing is there. So in that sense, when I'm going to illustrate, this will be much simpler, okay, and therefore the actual rules, which is what Hoare logic is meant for program verification, is more complicated. So I will take you ease you into Hoare logic that way. The program has branches, yes, okay, but it's just straight line in the sense it does not have loops. Okay, loops are quite challenging. Okay, one of the most difficult part of doing program verification. So this version of DNN, the feed-forward neural network, does not have loops, but there are variants of neural network models that have loops, like you must have heard of recurrent neural networks. So we may get into that as well as part of our reading assignment. So then the techniques that we'll be discussing for loops will also be relevant. Okay, I may not get to loops, how to verify loops in this lecture. Probably in the next lecture we will get there. So here's a quick overview. Okay, so each of these: pre is a predicate, post is a predicate. It's a predicate means it's a formula that defines a Boolean function over in the variables that are used in the program, which includes the input and the output variables. So predicate, I say that it characterizes a set of states, where a state is a value, assignment of values to the variables. Okay, so for example, here, this constrains v11 to be negative. Okay, doesn't say anything about the other variables, like the intermediate variables, which means at this point, what is meant is that those variables can be at this point, whatever arbitrary values. Okay, I mean, those other variables take on values as you execute the program. So at this point, so that's why this is denotes a set of states. Okay, anything that satisfies that predicate. Okay, any questions? No, okay. So then one way to do is you construct, okay, as opposed to the way that you did there, where you somehow magically using your ingenuity modeled it, okay, the behavior in terms of formula with some understanding of how a DNN behaves. Here, the program verification, you want to do that by analyzing every statement in your program, okay, one at a time. Okay, that is the that is the idea. So here, okay, this I've already mentioned. Yeah, I will get to that. Okay, that is how we are going to. So, yeah, so we are going to derive all those things. So that's my next step. How I'm going to be doing it. So the idea is to construct what I call as these are the strongest post condition after every statement in the program. Okay, starting from the precondition. So what is a strongest post condition? That is what I've defined here. So this is for every statement. It is relative to, it is defined in terms of the predicate that characterizes, that specifies the state prior to executing the program. So for example, here, this specifies the state of affairs before you execute this statement, okay? And so it's a predicate that defines precisely the set of states possible after executing that statement in a state after in a state that is satisfied after executing, starting from a state that satisfies this spread. Okay, that is when we define that. Here I'm defining what a strongest post condition is. This should capture, and that's what these question marks are. Okay, I mean these predicates that define the thing. So the idea is to construct these things. Okay, and they should capture exactly, precisely all the states that are possible that the variables can take at this time, and exactly those. Okay, that's when it will be defined as a strongest post condition. And I'll tell you how we'll do that. And that's what, and then you do that after every, I'll get your question. So you do that after every statement here, okay? And then after each state, okay, then when you get to the exit point, whatever the strongest post condition would capture, exactly, precisely that. Those set of states, the formula will characterize those set of states that can possibly occur at this point. But then we could use that to check that my post condition is satisfied by, if that is P5 here, I'll check validity of P5 implies post. Okay. Yeah, what is your question? Yeah. I'm going to fill these things, okay, in my next slide, and tell to give you an intuition as to how we could do that, and then I will. And the whole logic is a logic for, specifying these. It defines a set of sound inference rules to construct such predicates, okay? The strongest post condition as well as various other related concepts, okay? What do you mean by a typo? Yes. Yes, I thought I had removed it. Yeah, that's a typo. So here is, now let's start calculating SP, okay? And I'm going to do it kind of informally, okay? Bit of hand waving, okay? And then when I introduce the influence of the whole logic, it'll exactly tell you how I got these things. So VA11 is negative. So after I do this assignment, as per the semantics of my assignment statement, what does it do? It changes V21B. It makes V21B to be equal, the value of V21B to be equal to V11, and leaves everything else, including V11, unchanged. Correct? Which here was, I don't know, it was some arbitrary value. Okay, so here they all range over real numbers. They could be any real numbers. And that's exactly what it is. So V11 will continue to be less than 0. And V21B will be equal to V11. Okay, all the rest unchanged. Okay. And you can see that this is precisely, okay, the thing what happens, because that completely captures what the effect of this assignment is. Yeah. Why do I include V1, this part of the thing? No, but no. I want to, here I'm interpreting each of these as predicates standalone that describes whatever the state is at that point, okay? If I had not included this and only constrained this, then what will happen? It would have said V21B is equal to V11, but V11 could be anything. No? That's what that predicate will mean. But since I know that V11 was negative here and continues to be negative when I come here, that's why I want to have that. No? So, like I said, this should characterize after that assignment exactly the set by itself, okay, as things. So as you can see, each of them is a formula ranging, defined in terms of the variables. So if I did not have that, then it won't be constraining V11. So that constraint still applies. Okay, therefore it is important that you have the thing. Yeah. Your thing is, we could have a weaker. We can have a weaker post condition than this. Yeah, but then weaker post condition than that is yeah, speak up. So, of course, anything weaker, but that is still true is what you're saying, yeah? Weaker, that it is still true. Of course, you could say V11 is less than 0, okay? That is weaker, okay? It still is true at this point, okay, that V11 is less than 0, but it doesn't exactly capture the precise set of states. That's a weaker thing, okay? But it does not fully, and exactly capture the effect of this assignment statement, correct? Because this will also constrain V11 to be, V21B to be equal to V1. That's weaker, which is true at that point, but will not capture the exact thing. So that's why if you're doing it proof this way, okay, and you know, here I'm pushing through the strongest post condition, okay? So that I'll get the, yeah, that way, yeah, if I get the strongest post condition, then I know that is how do I do this? I have to figure this thing out. Okay, so I mean, advantage of carrying down the strongest post condition is it exactly tells me, you know, the exact state of affairs in the thing. Now, if I did something like what you said, it's unclear. Okay, if somehow V21B was never relevant, okay, the value of V21B was never relevant to the what you want to really check at the end. And if V21B was truly irrelevant, that was like a dead thing, then maybe using that weakest condition, weakest form of your thing would have sufficed, okay? But this is one way to guarantee that I could then prove any property that I want to have here. Okay, so we are kind of getting ahead, but those are good questions. Okay, so that is the idea. So similarly, what you do here is now you know that after you do this, these will remain the same, and V22B. Okay, will change. Yeah. Why is this the strongest? Why not? Yeah. I mean, you could say that, okay, in strictly speaking, this is what, if there is, okay, formally, if you want to do, okay, you will have to show that give me any other predicate, okay, that captures the values that any of these program variables can take, that is stronger than this. By stronger, you know, a predicate is strong, P1 is stronger if the set of things that it characterizes is smaller, okay? Smaller, that's what stronger means, okay? So is it? I mean, that's how you will answer then and convince yourself, okay? So that, of course, is very closely tied to the meaning of this, what exactly an assignment statement does. See, now that you bring the point, there is a subtle point here. Although it says here that all the other variables can take any value, what it does not capture, strictly speaking, is between here and here, all the other values may have whatever is at the input, an undefined thing, but they'll remain the same, okay? So in that sense, this is not the strongest, okay, since you brought up. So I've done a little bit of, I've been naughty a little bit, okay, that I've not captured. So if you really want to capture is, you have to say that, you know, whatever the value that the other variables had in here would be the same, okay? Now, I mean, there I'm nitpicking. So in that sense, okay, you know, you could say that it is not strongest. If you really want to do that, then what you'll have to do is you know, have all the initial variables, okay, and then say whatever it is, and then say carry along, okay. That kind of becomes a bit clumsy, and that's why I've left out. Usually the assumption is that there is something that says, oh, all the rest will happen, will remain the same as it is here, okay. So and so on, and since here it is all, well, okay, the interesting part will be where, you know, what do you do when you have an if then else, okay, statement. So here, what you have to do is you have to use this predicate, compute the strongest post condition for this predicate. Here, under the assumption V21B is less than 0, so you can add V21B and then get this, okay. So here I'm assuming that P2 prime has all these things and this, okay. And here, this and this one. Now, at this point, when I get out of the thing, there must be, I have to merge those two branches of if then else that do that. So P2 is true, okay? And if V21B is less than 0, then it is the case. And if V21B is not less than 0, that's the else part, then your V21F will be this one, okay? And that's how you do. And this is what Hoare rules will, when you see, will tell you how to do it for an arbitrary statement in terms of the strongest post condition that you compute for the components, okay? And you can see that this can be done very mechanically. This is actually you can write a program to generate. What is being done here is what I call as predicate transformation, okay? Given a formula that defines a predicate, you are, as per the rules of the semantics of your programming language, and there are only finitely many statements in your language, so they are all defined as a schema, as you can see, okay? And then like a compiler, you could write this, a program to do this. Okay, so this is fine. So similarly here, you will then define P4, okay? In terms of, P3. And by the way, this simplifies in this case to this one, because P2, as you can see with these things, the equality propagation, this becomes true, correct? V21B will be less than 0, and therefore it simplifies to this one. So that simplification is done. That's logical simplification. Z3 will do these kinds of things, okay? Yeah. Yes. Why is this here? Yeah, see, you should read all these what appears as curly brackets as annotations, okay? That is not part of the program, okay? The rest is part of the program code, okay? So this is something that I'm putting in as annotations to do this program verification, yeah? Yeah, so what I'm assuming here is when I'm here, prior to this, what is it that I can know? What is the pre of that? It's P2 and this, correct? Because P2 is already true there. And this expression, Boolean expression, does not have any side effects, okay? That I'm assuming in this case, there's no side effect. If it indeed has side effects, then it will be a different thing, okay? Therefore, P2 continues to hold good, and then I can be sure that V21B is less than 0, okay? So all these are program expressions, and what appears within braces are logical formulas, okay? And they share the same variables, okay? Technically, you should view them as different, okay, than this one. I'm using this logical variable to denote the value that that particular program variable holds at that point. Okay, but that conceptual difference is there, but I'm using the same thing. Okay, does that answer your question? Okay, so and now similarly I construct this, and here once again because of these things, one of the Boolean conditions will be false, and therefore this simplifies to this one. V21F will be 0, V22F will be equal to V22B. And finally, here, after this, I know that V31 is equal to minus V21F plus V22F. And based on all these equality, that simplifies to V31 to V22B. And V22B is minus V11, and minus V11 is negative, and therefore this will be positive, and that can be used to check that it is true. Okay. So here, of course, what you can blindly compute this P phi, okay, and then ship this formula to Z3, and it does all this equality propagation and things like that. Okay, so, and that's what we'll see. So this is, I mean, the same thing could be done in a backward direction as well. So there is a dual concept, two strongest post condition, which is called the weakest precondition. Okay, you can start from the post condition. Okay, then you ask the question, if this is what I want to be true at the exit point, what are the set of all states, okay, that, okay, start with the post, and you compute these predicates in the backward fashion until you get to this. In this case, it will be the weakest precondition that you will be calculating. Okay, so you know that I want V31 to be greater than 0. If I want V31 to be greater than 0, what are the set of all states, okay, that are permissible at this point, okay? Such that if I started in any one of them and executed this statement, that I'll be guaranteed to end up in a state which satisfies P5, which in this case is the post condition. That is the question that you know, I'll be asking, and that's what weakest precondition is. Weakest because it has to compute all the things. You know, it may be that I won't get to all of them under the input assumption. That's another thing. But here, since at this point I'm just propagating, I'm computing all the states that are permissible for me, you know, such that that I'm allowed to be in, such that this condition does not get violated. Okay, and similarly, I don't want to think, because I want to move to the general. So this is also possible. So as I said, this is called the weakest precondition, and then you do all this propagation, and then when you get to the weakest precondition at my entry point, then you will have to check if my assumption is within that permissible value. Okay, if it is, then I know that after I execute all these statements, then it will be there. Okay. No, this I'll get to later on. So I have 5 more minutes. these things. Because as I said, these kind of whole logic, it's very closely tied to a programming language, okay? Because you will see that just like in proposition logic, there was atomic formula, and then first order predicators started building the formula from atomic formulas. Here, the atomic formulas are what are called Hoare triples, okay? And they are a mixture of logical formula as well as program statements, okay? That's why it's a specialized logic for program that capture programming semantics. So to illustrate that, I'm just using a simple language, and these tools that mechanize Hoare logic and then do things, they work for C and all kinds of Java and all kinds of languages, okay? So that's it. So I don't want to, I've already illustrated some of these things. So correctness. So when I define these kinds of, okay, the correctness is defined with respect to pre and post, okay? So of course, pre and post are, but when I mean, this is kind of philosophical. When I say, is this correct or no? What does it mean? I mean, one is, it doesn't make sense just to ask this in the abstract. It means that what is your specification? What is your expectation? Only then I'll be able to answer it, okay? And there are so many things. You saw pre and post is one aspect of your expected behavior. So there could be lots of other things, okay? So like performance, performance and those kinds of things. And even within this, whether it termination as opposed to actually what it produces, whether it terminates, etc. There are so many aspects of the thing. That's what I wanted to think. So in this Hoare logic, it addresses two things, okay? There are two notions of correctness, okay? One is partial correctness. Yeah, so for every state that satisfies a precondition, if the program terminates with a state sigma prime, okay, then sigma prime must satisfy the post condition, okay? So it doesn't, so there are rules for getting proofs of this partial correctness. So total correctness also ensures termination. That for every sigma that satisfies the precondition, the program indeed terminates, and with a state sigma prime, and sigma prime would satisfy the post condition. Okay, and that's what this thing is. This is some historical notes. Okay, this is the basic what I call as judgment, and it's called Hoare triple. Okay, which is what I kind of showed you that. So here P and R are logical formulas drawn from some logic. They can be propositional logic, first order logic. We will be using first order logic because programs have data types and so on. So they are, but the variables are include the equivalent of the logical variables corresponding to the program variables. Whereas Q here is actual programming, a fragment of code. Okay, and that's what when I say this is true, what it means is if the assertion P is true before you execute at the entry point of the program, that is, if you're in a state in which that satisfies P, then if it terminates, if this one is usually the squiggly bracket is used to denote partial correctness. Okay, for the time being, let's assume that we are only dealing with partial correctness. Then, if it terminates, then R, it should be in a state in which R holds. Okay, so that's what this thing means. For every xy, such that Px holds, and the program Q terminates on X with output Y, then R of Y will be true. So if this is a non-terminating program, this is trivially true, okay? Then it doesn't matter. So keep note of that. For partial correctness does not address the thing, okay? So here with this, I will, with this slide, I will do. X is greater than or equal to 0. I mean, I've already given the answer. Then you do x is equal to x plus 1, x will be strictly greater than 0, correct? X is all, and skip is, why is this not true? Skip is a no-op, okay, a command. So if X is greater than 0, why is this not true? Anybody? Correct. What is that? Yeah, so the thing is that this itself, this predicate, does not constrain y in any way, okay? Therefore, as you said, y could be negative, and because this one does not change any variable, including y, so you end up being negative. That's the thing. So it's yeah, if X is true is a predicate, means that it does not constrain any of the program variables. So that's what true. False means that it is something that is, I mean, all these are predicates, okay, and they define sets of states, okay. So false defines the empty set, okay. What exactly it means for false to be the state of affairs, we'll see, okay. So what should this be? So X is less than or equal to Y, because if X is greater than Y, then it makes it to be equal, okay. And then otherwise you're not doing anything, and that's the case when X is anyway less than or equal to Y, and therefore it is less than or equal to Y. So here, these are some very interesting. So these whole triples that I have, even though I may not go through all of them, please review them, because they these are some examples that address certain corner cases, okay, that will help you understand the real meaning of these whole triples. Okay, so here's, asking, what is a program that can make this whole triple become whole, okay, become true? See, if this thing ever terminates, I say it's non-terminating because if it ever terminates, it has to end in a state in which there'll be some, it'll take some value, okay, correct? So, and since now I require that it be false, and false does not satisfy any state, okay? Therefore, in this partial correctness, this can only be non-terminating, okay? If it's non-terminating, then you can never get there, okay? And therefore, it could be anything, yeah. That is true. No. If it's non-terminating, you're right that the post predicate could be anything, okay? But including false as one of them, okay? Therefore, that's what I mean. So in this case, I specifically chose false. You're right, okay? Because that the semantics for all X, if it terminates the thing, if it's not terminating, then it is true, because logical implication is true when the precondition is false. So for a non-terminating program, you can plug in any predicate that you want in here, including false. Okay, so that's what this thing is illustrating. Yeah. Yeah. Similarly, here, this could be any predicate. Okay, because for the same reason. Yeah, because that's an implication. The meaning of the whole triple is an implication. And that implication, the precondition will be false, and therefore it'll be true no matter what. Okay, so you can plug in any predicate, and this will still be true, and so on. Okay, so I think I've run out of this thing. So I encourage you, since I want to move a little bit faster, if I can request you to just review the slides once, okay? Please review the slides. I may not cover all the slides. You may not understand all the slides. Nonetheless, just skim through the slides, and therefore I may be able to go a little bit faster. One other thing, next Monday, I have some family commitment, okay? So I want to, but I don't want to miss any class. So Tuesday, any time, okay, that is suitable to you, I'll do. So what would be the best time on Tuesday? Or you could, I mean, I can take a poll here and then it can be finalized. So say evening 5 o'clock, if there is, to avoid any conflict. Yeah? No? Well, I mean, I don't mind doing early in the morning, provided you guys are, early in the morning means what? How, when? Yeah, you see, anything very early, it'll be the thing. I don't mind doing 4 o'clock if that is, I mean, you don't want in the afternoon itself. You prefer in the morning, is it? Why don't you, yeah, through a WhatsApp thing. Or we could do Wednesday also, which. So do you have a class now? So, but I, yeah. You want to move, you are the one who had asked the Friday class to be moved. I'm okay with that, but Friday move it to when? Yeah, but the thing is, on Friday, 3:30, I don't think this is available, okay? So that's a problem. And then we have to do in the seminar hall because no other hall, the NKN hall is there, but that is even more complicated. I don't want to, I mean, the equipment there is very, very complicated and there are all kinds of variables. It looks like lunar mission is easier than that, that technology there. Okay, so I want to stick to this. So I don't mind moving it, but there are two things. Okay, when to move the Friday class to, okay, and the other one is when to have the replacement class for Monday. Okay, but if so, okay, so Tuesday at 5 is the tentative thing that we'll have. Okay, thank you. Your German when at 5? Yeah, I think then we will decide. I'm free on Tuesday. Even if Tuesday is not possible, Wednesday is also a possibility. Yeah. So,